Okay, 1-to-1 means that both the function and its inverse are functions, or there is only one y for every x. So you can use your calculator for these, but I'll make a sketch by hand. So 2x minus 5 is a line, so yes, that is 1-to-1. Negative x squared looks like this. So the inverse, you could tell, is not going to be a function because the horizontal line test touches the equation twice. You use the same thing for absolute value of x. The original is a function, but the inverse is not, so it's not 1-to-1. X to the third minus 9x. We're going to graph that. This is one I'm going to use my calculator for. So I'm going to graph x to the third minus 9x. I'm going to look on a standard window. So this one is also not 1-to-1 because it will fail the horizontal line test. Okay, to verify algebraically if functions are inverses, we need to show that f of g of x equals x and g of f of x simplifies to x. We have to show these two. So f of g of x, so that's 7x minus 6. But instead of x, I have to put the equation. And now to simplify, these cancel. And I'm left with x plus 6 minus 6, and that simplifies to x. We can do the same thing this way. So we have x plus 6 over 7. Negative 6 and positive 6 are 0. So 7x divided by 7, that equals x. So yes, they are inverses. Which of the following is an inverse of that function? So I can actually find the inverse of this by switching x and y. And solving for y. So I'm going to subtract the 5 to the other side. And now to move the 1/3, I'm going to multiply this side by 3 so that these cancel, and everything here by 3. So we get 3x minus 15 equals y. And that answer is D. So we're going to use the same process to find the inverse of this function. Switch x and y and solve for y. So I'm going to add 10 to both sides. Then I'm going to divide everything by 9. So I have x over 9 plus 10/9 equals y, which, using the inverse notation, the inverse of the g function is this equation. To determine if the sketch the inverse, I have to switch every x and y. So this point is at 1, 3, so I'm going to graph 3, 1. And this point is at 4, 6, so I'm going to graph 6, 4. And then lastly, this point is at 1, 2, 3, 4, 5, 6, 7. This is at 7, 8, so I'm going to graph 8, 7. 0, 0, when I switch that, is still 0, 0. There's the inverse. I'm going to use the same process here. This point is at negative 7, 2, negative 3, 3, 0, 5, and 2, 8. So I need to graph 2, negative 7, 3, negative 3, 5, 0, and 8, 2. And connect the dots. Looking at this graph of the absolute value, it's moved to the right 3, no, I'm sorry, to the left 3, and up 4. Let's make that graph bigger. So the vertex is at negative 3, 4. So to make this graph a function, we need to restrict half of it so that when the inverse, to make the inverse a function. So I could say there's two possible answers. Either x needs to be greater than or equal to negative 3, or x could be less than or equal to negative 3. Both answers are correct. Describe the transformations. So we start already to the right 2. So this vertex is at 2, 0 for the original. The vertex of 25 is at 0, 1. So how did we go from to the right 2 to 0? That's left 2 units and up 1. This vertex is at 3, negative 9. So to go from 2, the start, to 3, we went to the right 1. And then down 9. And this 5 in the front is a vertical stretch of 5.